So guys, let's get started by actually discussing how ACER tests systems equilibrium. So with systems equilibrium, I think it's important to understand two fundamental principles, right? So the first principle is that there are vector quantities, and there's not just one vector quantity, there are multiple vector quantities. So the first principle is that you need to identify all the relevant vector quantities based off of the question stem that you're currently interrogating. There's a quick and simple rule that I utilize to help with this, and I think it's very effective for basically everyone. So the first and most fundamental vector unit is displacement. So I'm going to use this triangle to outline the fact that it's a difference, okay? And delta x, right? So delta x stands for displacement, which means basically how far you have been removed from your initial starting position. So it's not distance, which is a scalar unit, it's a vector. Displacement, which is how far you've been moved from your initial starting position. So we start with delta x. And to get from delta x to velocity, right, you have to divide this by time, okay? So time itself is not a vector quantity. However, it is an important consideration for the equations, which you'll see next, right? So delta x divided by time is equal to velocity. And then velocity divided by time is equal to acceleration. And acceleration times mass, okay, is equal to force. So your vector quantities are these ones, okay? Displacement, velocity, acceleration, and force. And your non-vector quantities, quantities that are still helpful but not vectors, are your times and your mass, okay? Some other points that you need to elicit as well. So with velocity and also with displacement and even acceleration, right? Velocity, displacement, acceleration, in particular velocity, there are two aspects to velocity. There is initial velocity, so your starting velocity, and then your final velocity, right? So you need to be mindful of this when you're doing questions. Initial velocity means the speed that you start with. Final velocity is the speed that you either accelerate to or decelerate to by the end of the question. And as you can clearly notice, it's to do with acceleration, right? With acceleration as well, you just always need to assume this. Acceleration due to gravity is always negative 10 meters per second squared, okay? Meters per second squared. So the reason why it's per second squared is because you're dividing by times twice, right? Okay, so these are some of the background concepts that you also need to be wary of. Okay, so the first principle is know every single vector quantity that the question is possibly asking you to examine. The second principle, right, is then select the equation, right? Select the relevant equation, the relevant mechanics equation or systems equilibrium equation that will isolate you to simply one independent variable. And what do I mean by one independent variable? I mean, when you are given these questions, you will be given a list of formulas as well, right? So here I've just, pulled out four of the fundamental formulas for mechanics, okay, based off of my own personal notes, right? But if you look at some of the other questions that you'll see below, here are three questions. Here are three mechanics equations that this question stem has provided for you, right? So when you are given an array of equations to choose from, okay, you need to select the one equation that only has the one independent variable, the one unknown vector quantity that you are seeking to solve, right? So these are the two fundamental principles of vectors. Having said that, let's now go and solve this question in particular, all right? Let me minimize these notes, right? So that we can actually go and solve this question. All right. Now, when you're solving said questions, I'm going to try and introduce a new way of thinking, a new way of diagram annotation. So remember, when you're doing questions, there are rules. In this particular instance, these are the two rules that you've got to be mindful of. And then the second thing is that there are diagrams, right? So when you're diagramming, right, um, vectors, it's very important for you to establish planes. So X planes and Y planes. And the reason why is because vectors have directionality and vectors have magnitude. So if you were to break vectors down into its x and y components, that's how you'd have to label it, right? And the benefit of labeling it in such a manner is that what vector quantities, you know, are not apparent on text, when you diagram it, further information might be elicited about these, non-visible vector quantities, right? So I've spoken enough. Let's just do this question now. All right, so problem set A. A child falls from a bunk bed that is 2 meters tall. The child weighs 45 kilograms. Write an expression for the velocity of the child as he strikes the floor. So here's a bunch of, you know, text. Let's translate this into a corresponding particle flow diagram. Okay, so we've labeled the diagram y, x. Let's make the bed, right? So the bed is how long or how tall? So the vertical displacement, right? Delta y, vertical displacement, is -2 meters, right? The child is initially on this bed, right? And then the child falls, right? Now, the question's asking you for the final velocity of the child, okay? Remember, velocity is broken down into initial and final. In this situation, you can make it even more clear with the fact that velocity can exist as a child rolls left to right, which is in the x plane, or in this particular context, we are concerning ourselves with the y plane. Everything is vertical in this context, right? So the velocity of the child as he falls, okay, falling occurs in the y plane. That is our independent variable. That's our unknown, okay? So what other information can we elicit? Okay, so the other information is that the velocity of the child, so the initial velocity of the child in the y plane, right? How much should that be? Okay, so VIY, the initial velocity of the child should be 0 because when the child is on top of the bed, he's not jumping up and down. He might be tossing left and right, but the initial velocity in the y plane is 0, right? And what is the other assumed information you must always consider? That acceleration due to gravity is -10, okay? So acceleration in the y-axis is -10. Okay, so using our table, we know the displacement, we know the initial velocity, we don't know the final velocity, we know the acceleration, and we know the mass. We don't need to know force. It's not asking us about force, right? So what's the other quantity that's unknown? The other quantity that's unknown is time. So here we have two independent variables, right? So that is why we get to that second principle. We need to select the equation that only has a one independent variable, right? So we can't select an equation that has both VFY and time together because in that case, you've got two unknowns and you can't solve that equation, right? So let's go down to these following formulas. So what formulas do we have? VF equals VI plus acceleration times time. So for instance, equation one, we can't use because it's got time and VF, both of which are unknowns. Equation 2 has VI and time, but it doesn't have VF, and VF is, the intended independent variable that we're trying to solve here. Equation 3 has VF, but it again has time. So the only equation that we've got left is the fourth and final, 2a delta x equals VF squared minus VI squared. So notice here, we have VF, which is our unknown, and we don't have times, right? So we can now solve it. So 2 times acceleration, which is -10, times -2 for our displacement in the vertical is equal to VF squared, which is unknown. I'm just going to write VF squared, right? Minus VI squared, which is 0. So 0 squared is equal to 0, right? So what is the expression? VF squared. So 2 times -10 times -2 is equal to 40, right? So VF is equal to the square root of 40 meters per second. Okay, so that is the expression of the child as he strikes the floor. That's the speed at which he's traveling.